Okay, this problem is very much the same as the previous one. Again, we've got an air conditioning duct, but with a few differences. The first difference is that the length is 40 meters, so it is a shorter duct than with the previous problem, 40 meters. The other difference is that the volume flow rate is much lower. The volume flow rate is equal to 0.01 cubic meters per second. Again, the surface temperature of the duct is 40 degrees Celsius, so it is in an attic, and it's an uninsulated duct. The duct dimensions are 400 by 600, like that. 600 there, 400 there. And the air inlet temperature is 10 degrees Celsius. Okay, it is air, and it is at approximately 1 atmosphere of pressure. So let me just repeat the problem. It's an air conditioning duct. The inlet temperature of the air is 10 degrees Celsius, pressure of approximately 1 atmosphere. The duct on the outside is at a constant surface temperature of 40 degrees Celsius. The volume flow rate to the duct is equal to 0.01 cubic meters per second. The length of the duct is now shorter than the one that I've done in the previous problem, is 40 meters. The dimensions of the duct again is 400 millimeters by 600 millimeters. And we are required to determine the outlet temperature, the heat transfer rate, and the pressure drop through the duct. Now, in the theory class, we've done it already that with this type of problem, we have the following. If we look at the temperatures as a function of x. Firstly, we've got the wall temperature of the duct. There it is. And that is the warmer one of the two, and that is at 40 degrees Celsius. So Ts is 40. So the temperature there is equal to 40, and the temperature there is equal to 40. And we've got the air at an inlet temperature of 10. Okay. And we've got a certain outlet temperature here, Te. Now what we do not have, and that is the very important thing with this type of problem, is that the temperature of the air increases linearly. And that we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by this temperature difference. We've already derived it in the theory classes that when we have a constant wall temperature, that the temperature profile on the inside would not be linear, but would be exponential. So it would be something like that. So where previously we've calculated the bulk temperature as the average between the inlet and the outlet temperature, and then use that delta T to calculate the heat transfer rate, we can now see that that is not going to be effective here. The average temperature difference is not that temperature difference, it is something else. And we have actually already derived it, that the outlet temperature can be derived as the surface temperature minus the inlet temperature of the stream, e to the minus NTU. NTU is the number of transfer units, and the number of transfer units is equal to the heat transfer coefficient multiplied by the surface area of heat transfer divided by the mass flow rate and the Cp of the stream. And the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the LMTD. The LMTD is the log mean temperature difference. And specifically what we cannot do is to say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the average temperature difference, which is Ts minus Tb. So that is not an accurate and a good approach, and we cannot use that. And that's the reason why we've actually derived this temperature profile and the heat transfer rate as a function of not the average temperature difference, but as a function of the LMTD. So if we look at what we have to calculate the outlet temperature Te of the air, we have to calculate the heat transfer rate and the pressure drop. Now, to be able to do that, the things that if we just look at these equations, that we will have to calculate is, we will have to calculate the NTUs, and to calculate the NTUs, we need the surface area of the duct, we need the heat transfer coefficient, we need the mass flow rate, yes, we need the CP, but to get the heat transfer rate, we will have to get the Nusselt number. And before we can get the Nusselt number, we need to know if the flow is laminar or turbulent. So we also need to calculate the Reynolds number. So those would typically be the things that we need to calculate before we can solve this problem. And obviously we also will have to calculate the friction factor so that we can calculate the pressure drop delta P. So there's no specific recipe that we can follow in terms of a specific logic, in terms of what we should calculate before we can get all these values. It is sort of a little bit intuitive. Right, now if we look at what we need to calculate, one of the most important things that we always need is we will need properties, and we will need the properties of the air, such as the density, the CP values, the viscosities, etc. And to be able to do that, we need to go and look in tables, and if we look in tables, we will see that the properties are a function of temperature. So we need to decide on a very good representative temperature for the air. So if we want to calculate the properties of the air, we normally do it at the bulk temperature. And the bulk temperature, if we come back to the sketch, is the average between the inlet temperature and the outlet temperature. So it is Ti, the inlet temperature, and the outlet temperature divided by 2. Now we have the inlet temperature, but we do not have the outlet temperature. So in cases like this, what we do is we just guess an outlet temperature. Now you can make your own guess, but if I look at this, I can obviously see that the outlet temperature cannot be lower than 10, it cannot be higher than 40 degrees. So what I'm going to do is I'm going to guess an outlet temperature of 30. So that is just an assumption. So 10 plus 30 divided by 2 is 40 divided by 2 is 20 degrees Celsius. So I'm going to get the properties of air at 20 degrees Celsius. And you can go and get it on the internet, or you can go and get it from textbooks. In our case, we are using the textbook of Sengel and Gejar. So in the textbook of Sengel and Gejar, the properties of air at 20 degrees Celsius are given in table A15. So from table A15, I've obtained that the density of the air, which will be equal to 1.204 kilograms per square meters. The CP is equal to 1007 joules per kilogram Kelvin. The thermal conductivity of the air K is equal to 0.02514 watts per meter Kelvin. The viscosity of the air is equal to 1.825 multiplied by 10 to the minus 5 kilograms per meter second. That is the normal viscosity. The kinematic viscosity, which is the viscosity divided by the density, is equal to 1.516 multiplied by 10 to the minus 5 square meters per second. And then lastly, the Prandtl number is equal to 0.7309. So those are the properties of air. It is at the temperature of 20 degrees Celsius, density 1.204, CP 1007, K of 0.02514, the viscosity of 1.825, the kinematic viscosity, which is the viscosity divided by the density, is equal to 1.516 multiplied by 10 to the minus 5. and the Prandtl number is equal to 0.7309. Right, now with that, there are a few other things that is also handy if we can calculate it before the time. And that is firstly the cross-sectional area. So the cross-sectional area is the area through which the flow occurs. So if that is the duct and that is our air flowing through it, then that would be the cross-sectional area, AC. So the cross-sectional area AC would be, and that is 600 millimeters and that is 200 millimeters. Then that would be equal to 0.6 multiplied by 0.2, and that is equal to 0.12 square meters. Okay. Then also the perimeter. The perimeter would be equal to 0.2 plus 0.6 plus 0.2 plus 0.6, and that would be equal to 1.6 meters. So the perimeter is just this outside length, 0.2 plus 0.6 plus 0.2 plus 0.6, right, 1.6 meters. The other area that is also very important is the area for the heat transfer, through which the heat transfer will occur. So on the outside we've got the air at 40 degrees, on the inside we've got the cooler air, so the heat transfer rate is going to occur through this area here, through those four sides. Okay, and we call that the surface area, AS, which is now different than the cross-sectional surface area. So the surface area is the area through which heat transfer will occur. That would be the perimeter, which is P, multiplied by the length. The perimeter is equal to 1.6, we've already calculated it, and the length of the duct is 40 meters, so the cross-sectional area is 64 square meters. Right, so that is the other area that we need to calculate. The other thing that is also very important to calculate is to calculate the hydraulic diameter. Why? Because the non-dimensional groups such as the Reynolds number and the Nusselt number that we're going to use, all of them have been developed for a cross-sectional area. And if we have another type of cross-sectional area like we have at this stage, which is 600 by 200 millimeters, we need to make use of the concept of the hydraulic diameter to transform this geometry to that of a circular cross-sectional area. And we do that by calculating the hydraulic diameter. And the hydraulic diameter by definition is 4 times the cross-sectional area divided by the wetted perimeter. Take note, not only the perimeter but the wetted perimeter. So it is equal to the 4 times the cross-sectional area. The cross-sectional area we've already calculated as 0.12, so it is 4 times 0.12 divided by the perimeter. And now we have to be careful here, it is the wetted perimeter. Now because we have air flowing through this duct, it will be in contact with all 4 of the sides. So the previous perimeter that we've calculated as 1.6 will indeed be the wetted perimeter. So if we go and calculate the hydraulic diameter, it would be 0.3 meters. So it would mean that in terms of the calculation of the Reynolds number and the Nusselt number, we have to base it on the hydraulic diameter. Okay, and the hydraulic diameter would be this characteristic length of 0.3 meters. Right, now before we can calculate the Reynolds number, we need the velocity, because the Reynolds number is equal to the density multiplied by the velocity multiplied by characteristic length divided by the viscosity. Okay, now we do not have the velocity at this stage, So we need to calculate it, and we can actually calculate it by first calculating the mass flow rate. The mass flow rate of the air would be equal to the density multiplied by the cross-sectional area multiplied by the velocity, or we can write it as the density multiplied by the volume flow rate. So this V with a strike through is what I'm using for the volume flow rate. So the density is equal to 1.204, and the volume flow rate has been given as 0.01, and that gives us then a mass flow rate, if we can calculate it, as 0.01204 kilograms per second. And that's an important one, so let's put some red underneath it because we're going to use it somewhere else also. Right, now that we've got the mass flow rate, we can also calculate the velocity. So from the same equation, the mass flow rate is equal to the density multiplied by the cross-sectional area multiplied by the velocity. The mass flow rate has been solved as equal to 0.01204 is equal to the density, which is equal to 1.204, multiplied by the cross-sectional area, which is equal to 0.12 multiplied by the velocity. So now we can solve the velocity of the air as equal to 0.0833 meters per second. Right. Okay. And now that we've got that, now we can go and calculate the Reynolds number. The Reynolds number, as I've said previously, is equal in general is equal to the density multiplied by the velocity multiplied by a characteristic length divided by the viscosity. Right. Now in this case, the characteristic length is going to be our hydraulic diameter. So we calculate the Reynolds number as a function of the hydraulic diameter is equal to the density, which is equal to 1.204. The velocity that we've solved just now is equal to 0.0833. Now the characteristic length now will be the hydraulic diameter, which is 0.3 divided by the viscosity, which is equal to 1.825 multiplied by 10 to the minus 5, and that gives us a Reynolds number of 1650. Right. Now because this Reynolds number based on that of a circular tube is less than about 2100 to 2300, we know that the flow would be laminar flow. Right. And for laminar flow for a circular smooth tube, right? So if it's a circular smooth tube, if it's laminar, then we've already derived in the theory class that the Nusselt number would be equal to 3.66. So this is a very simple problem now. We can just say, well, we've got the Nusselt number, the flow is laminar, it is equal to 3.66. However, we have to be very, very careful. That is not really that correct. If we go to the theory of flow through ducts and tubes, we will be able to see that, and I'm going to move to this section now, to this side here, that a lot of analytical work has been done for different types of geometries to get the heat transfer rates and the Nusselt numbers and the friction factors. For example, in the textbook that we are using, the textbook of Sengel and Gejar, and there are many other textbooks that can be used and also the internet, but typically in table 8.1, if the flow is laminar, in that textbook you will see that if we've got a duct like the one that we're considering at the moment, then they give the properties as a function of A and B, and they would give then the Nusselt number for constant wall temperature, they would give the Nusselt number for the case of a constant heat flux, and then they would give the friction factor. Okay. And if the ratio of A to B is 1, then the Nusselt number will not be equal to 3.66, it would be equal to 2.98 if it is a constant wall temperature case. If it's a case of constant heat flux, then the Nusselt number would be equal to 3.61, and the friction factor would be equal to 56.92 divided by the Reynolds number. Okay, now this is not the case that we are looking for. We are looking for the case of A divided by B. A is 600 millimeters, B in our case is 200, so that is the case of A divided by B of 3. So for this specific case, then the Nusselt number would be equal to 3.96. So you'll see it is not 3.66. It's a little bit higher. It's not that much higher, but it's not 3.66, so it's 3.96. And that would now be for the case of a constant wall temperature, as we have. If it was a constant heat flux case, then the Nusselt number would be equal to 4.79. And the friction factor is equal to 68.36 divided by Reynolds number. Now in this table 8.1, I'm not going to give you a summary of all the results, but you will also see that if the cross-sectional area is that of an ellipse, and again the ellipse with an A and B ratio, if the A divided by B ratio typically is equal to 4, then the Nusselt number would be equal to 3.79. And then lastly, if we've got a triangle typically like that, and depending on that angle there, theta, typically if the angle theta is equal to 90 degrees, then the Nusselt number will be as low as 2.34. And the friction factor would be 52.60 divided by the Reynolds number. So that is in general information that we can get from textbooks for laminar flow, and it's very relevant to this specific problem, because what we have now in this case is we have to, from this table, obtain that the Nusselt number would be equal to 3.96 and not equal to 3.66 as we will have for a circular tube. Right. Now, the other thing that is now very important to remember is that this Nusselt number is for a Nusselt number where we have fully developed flow. Okay. So if we look at the flow through the duct, if that is the flow there, then the question is how much of the flow is fully developed and how much is developing. And for us to be able to calculate that, then it is very easy. We can say LH is equal to 0.05 multiplied by the Reynolds number multiplied by the Prandtl number multiplied by the hydraulic diameter. Now LH is how long it is going to take for the velocity profile to fully developed. So that is equal to 0.05 multiplied by the Reynolds is equal to 1650 multiplied by the Prandtl number, which is equal to 0.6. Sorry, there's no Prandtl number in there. I have to take that out. It is just equal to 0.05 multiplied by the Reynolds number multiplied by the hydraulic diameter. So equal to 0.05 multiplied by the Reynolds number 1650 multiplied by the hydraulic diameter, which is 0.3. So if we calculate it, then it is 24.75 meters. And LT will be the length, how long it is going to take to develop fully thermally, and that would be equal to 0.05 Reynolds number Prandtl dH, or we can just write it as that length multiplied by the Prandtl number. So it is equal to 25.75, and the Prandtl number is smaller than 1. It is equal to 0.7309, and that therefore means that the flow is going to take just 18.09 meters before it is developed fully thermally. So if we just now look at this duct of us over a length of 40 meters, there's 40 meters, and let me draw the duct there schematically again. If we now look at this length, so that would be about half. Let's suppose that is about 24 meters there, 24.75. So it means that it will take 24.75 meters before the velocity profile is fully developed. So it will be a parabolic velocity profile like that, and 18 meters is less than half, so it is, let's suppose, about there, about 18.09 meters. So that would be there, and it would mean that the temperature profile would be fully developed at that position there. So why is that important to our problem? It is important to our problem because we have to realize that this Nusselt number of 3.96 has been derived for fully developed flow. And we will have fully developed flow only after 18 meters. So it would be for a little bit more than half of the length, the Nusselt number would be equal to 3.96. So we have solved about half of the problem. We know the Nusselt number in that part of the duct, but we do not know what the Nusselt number is here. So let's do it like that to show that we still have to determine what the Nusselt number must be here. So that is an unknown to us at this stage. So with that known now, we have two approaches that we can follow. Okay. Approach one is to make the assumption, which would not be that accurate, to make the assumption that the Nusselt number is equal to 3.96 for x larger than 0 and smaller than 40. So it would mean that for this whole duct of us, we're going to make the assumption that the Nusselt number is a constant right through. And we can see that that is obviously not that accurate. It must be a little bit higher. We don't know how much higher, but it must be higher. But it is just an assumption. So let's suppose we make this assumption, then we can say, well, the Nusselt number based on the hydraulic diameter is equal to the heat transfer coefficient multiplied by dH. That is why I've got the hydraulic diameter here, hydraulic diameter for the H there, divided by K. So the Nusselt number based on the hydraulic diameter is the heat transfer coefficient multiplied by the hydraulic diameter divided by K. The Nusselt number we have solved now is not solved, but we've got it from the table, is equal to 3.96, and it's an assumption that that is the Nusselt number right through the duct, is then equal to the heat transfer coefficient multiplied by the hydraulic diameter, which is 0.3, divided by the thermal conductivity of air, which is equal to 0.02514, and that gives us a heat transfer coefficient of 0.3318 watts per square meter degree Celsius, watts per square meter Kelvin, it doesn't matter. Right, now we can calculate the NTUs. The NTUs is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the CP. We've already calculated all four of these variables. The heat transfer coefficient is equal to 0.3318. The surface area through which heat transfer occurs is 64. The mass flow rate is equal to 0.01204, and the CP value of the air is 1007, and that gives us an NTU value of 1.752. Right, now that we've got that, we can calculate the outlet temperature of the air from the equation that we've previously derived, which is the outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus NTUs. Okay, and that is the surface temperature is 40 minus, again, the surface temperature is 40, the air inlet temperature is 10, e to the minus NTUs, and the NTUs has been calculated as 1.752, and that gives us an outlet temperature of 34.8 degrees Celsius. Now, if we do calculate something like that, let's just go back to the graph. Does it make sense? Yes, it is not higher than 40. Then we know that we've done something wrong. It is lower than 40. It is higher than 10. So it really does make sense. Right. Now, if we want to calculate the heat transfer rate, as I've already discussed, we cannot say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the average temperature difference, because we've got this temperature profile. we need a better representation of the average temperature difference. And we do that with the log mean temperature difference. And if we want to calculate the log mean temperature difference, I will always recommend just make a sketch, a very simple sketch. And the sketch is then the sketch of the wall temperature, which is 40 and 40, and the inlet temperature, which is 10 of the air, and now the outlet temperature, which is 34.8. Now, because we have all four the temperature values, it is very simple to calculate the LMTD, because the LMTD is equal to this temperature difference, 40 minus 10. Let's write it down, 40 minus 10 minus this temperature difference, 40 minus 34.8. And now what we do is, it's the lim of those two terms, 40 minus 10 and 40 minus 34.8. Okay, so let me just repeat again. The LMTD is the temperature difference at the inlet. The inlet is 40 minus 10 minus the temperature difference at the outlet, which is 40 minus 34.8, divided by the lim of the first term, the inlet temperature difference, term, divided by the outlet temperature difference term, 40 minus 34.8, and if we can calculate the temperature difference, it is equal to 14.16 degrees Celsius. Right, now it is very simple to calculate the heat transfer rate. So the heat transfer rate is now equal to the heat transfer coefficient multiplied by the surface area multiplied by LMTD. Take note, not the average temperature difference, as I've discussed now many times. So the heat transfer coefficient is equal to 0.3318 multiplied by the surface area, which is 64, and the temperature difference, which is 14.16, and that gives us a heat transfer rate of 301 watts. Okay, now that was actually the complicated way of calculating it. We could have also calculated it from just looking at what happens with the air stream, which is being heated from 10 to 34.8. Okay, because we could have said it is equal to the mass flow rate of the air multiplied by the Cp of the air multiplied by the outlet temperature minus the inlet temperature. So the mass flow rate of the air is equal to 0.01204. The Cp value is 1007. The outlet temperature is 34.8 minus 10, and that gives us a heat transfer rate of 301 watts, and they are the same, so we can feel very comfortable of our result. So that is the first approach that we could have followed of calculating the heat transfer rate through this duct. Not the best of the most accurate method, but just getting an order of magnitude approach would be totally valid. So let's use a second approach, and with the second approach we're going to try to be more accurate. So with the second approach we want to take into consideration, so approach 2, take into consideration the developing flow. Developing flow. Remember, this is the developing flow, and this is the fully developed flow. Fully developed. Okay. Now, when the flow is fully developed, the Nusselt number is 3.96. If it is developing, it is higher, but we do not know what it is. So the problem would now be of getting the Nusselt number for this regime, taking into consideration the developing flow, or an equation that gives the average Nusselt number for this whole flow regime. Well, if you're going to look in your textbook, you will see that there's an equation of Edwards. And the equation of Edwards looks like this. It gives the Nusselt number as 3.66 plus 0.065 multiplied by D divided by L multiplied by the Reynolds number and the Prandtl number divided by 1 plus 0.04 multiplied by D divided by L multiplied by the Reynolds number and the Prandtl number to the power of 2/3. So that is typically how the Edwards equation looks like. Now the Edwards equation is an equation which is an equation, and that is very important. We have to read the fine print. It's an equation that has been developed for a circular tube, and it takes into consideration the developing flow, and if we would calculate it over 40 meters, it would give us the total average over the 40 meters. And it also shows that if the tube is very, very long, that this equation will reduce us to a Nusselt number of 3.66. Now, what we have in this case is we do not have a circular tube. We have made use of the approach of the hydraulic diameter, where we've changed this geometry to that of a circular tube. But we can immediately see we do not have a value here of 3.96, but of 3.66. So this equation is not really exactly valid, but I'm going to manipulate it a little bit by changing that value to 3.96. So it would mean that if this tube is very, very, very long, maybe 1,000 meters, then the Nusselt number, this part of the tube would be so small in comparison with the total length that the average Nusselt number would be 3.96. So this is not really a change that I can justify. All I'm just trying to say is that you will have to go and look at literature. You will have to go and look for this specific geometry and see if you can get an equation that takes into consideration the developing flow, and normally it would be of this type of format. So what I'm going to do now is I'm going to make the assumption that I can calculate the average Nusselt number over this total length, taking into consideration the developing flow with this equation. So let's do that, and that would then be the Nusselt number is then equal to 3.96 plus 0.065 multiplied by 0.3, the hydraulic diameter, divided by 40, multiplied by the Reynolds number, which is 1,650, multiplied by the Prandtl number, which is equal to 0.7309, and divide it all by 1 plus 0.04, multiplied about by the same variables, 0.3 divided by the length of 40, divided by the Reynolds number of 1,650, multiplied by the Reynolds number, the Prandtl number of 0.7309 to the power of 2/3, and the Nusselt number that I've obtained now is 4.461. Okay, so this Nusselt number is very important. It is the average over this total length of 40 meters. So it gives us this average value here. So if we can get an equation like this that can now calculate that Nusselt number for us, which is equal to 4.461, then that would be great. That is actually what we want to get in principle for this type of problem. So if we've got that Nusselt number now, then we can say, well, the Nusselt number based on the hydraulic diameter is equal to the heat transfer coefficient multiplied by the hydraulic diameter divided by the thermal conductivity of the air. The Nusselt number, we've obtained it as equal to 4.461, equal to the heat transfer coefficient multiplied by the hydraulic diameter, which is 0.3, divided by the thermal conductivity, which is equal to 0.2514, and that gives us a higher heat transfer coefficient than previously, which is equal to 0.3738 watts per square meter degree Celsius. All right, now that we've got the heat transfer coefficient, we can calculate the NTUs. So the NTUs is equal to the heat transfer coefficient multiplied by the surface area divided by the mass flow rate and the CP. And we've already discussed it in the theory class. if the NTUs is equal to 5, then you can actually expect that the air temperature would be equal to the surface temperature. And if it is approximately 3, then it will already be about 90 to 80% of the surface temperature. So let's see what we're going to get here. So the NTUs is equal to the heat transfer coefficient, which is equal to 0.3738, multiplied by the surface area. The surface area is 64, divided by the mass flow rate, which is equal to 0.01204, divided by the CP, which is 1007, and that gives us an NTU value of 1.973. So it is almost 2, which means that we can actually expect quite a significant increase in the temperature of the air. And with that, we can now calculate the outlet temperature of the air with the equation that we've derived in the theory. The outlet temperature is equal to the surface temperature minus the surface temperature minus the inlet temperature, e to the minus NTUs. Okay, now the surface temperature is 40 minus, again the surface temperature is 40, the inlet temperature is 10, e to the minus NTUs is 1.973, and that gives us an outlet temperature of 35.83 degrees Celsius. Okay, previously, if we just go back to the previous case, outlet temperature was about 34.8, which is about 35. Now the outlet temperature of the air is going to be higher. It's going to be about 36 degrees Celsius. Again, if we want to calculate the heat transfer rate, we need to have a very accurate description of the temperature difference between the surface wall temperature and the air temperature. Again, I would recommend draw the sketch. The wall temperature is 40 and 40, the inlet temperature is 10, and now we've calculated the outlet temperature as 35.83. So again, let's calculate the LMTD. The LMTD is equal to this temperature difference, 40 minus 10, there the inlet, 40 minus 10, minus the temperature difference at the outlet. The outlet, it is 40 minus 35.83 divided by the lim of those two terms, 40 minus 10 and 40 minus 35.83. Okay, let me just repeat it again. The LMTD is the temperature difference there, 40 minus 10, minus the temperature difference at the outlet, 40 minus 35.83, divided by the lim of those two terms. And if we go and calculate it, then the LMTD temperature difference is equal to 13.09 degrees Celsius. All right, now that we have that, it is very easy to calculate the heat transfer rate, and there are two methods that we can use to do that with. Firstly, we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by LMTD. Right? The heat transfer coefficient we've already solved is equal to 0.3738 multiplied by the surface area for heat transfer, which is 64, multiplied by LMTD, which is 13.09, and that is then a heat transfer rate of 313 watts. While on the air side, again, we could have also calculated it as the mass flow rate multiplied by the CP multiplied by the outlet temperature minus the inlet temperature. So this is the air side, so that's the air, and that is the wall. Okay, on the air side, the air has been heated from 10 to 35.83, so it is very easy to say that the heat transfer rate is equal to the mass flow rate multiplied by the CP multiplied by the delta T, and that is then equal to the mass flow rate, which is equal to 0.01204 multiplied by the CP, which is 1007. The outlet temperature is 35.83 minus 10. And again, the transfer rate is 313 watts. So, if we now look at the second approach in comparison with the first approach, With the first approach, we've calculated the outlet temperature as about 34.8 and the heat transfer rate as 301 watts. With the second approach, we've seen that the outlet temperature is higher. Why? Because of the higher heat transfer rate through the developing part. So that is the reason why the temperature is higher, and therefore the heat transfer rate is then also a little bit higher than that where we've made the assumption that the heat transfer coefficient is constant right through the tube. Right, so we've calculated now two of the three things that were asked of us. So if we go back to the problem, we were asked to calculate the outlet temperature, to calculate the heat transfer rate, and the pressure drop. So the last thing that we need to calculate is the pressure drop. Now the pressure drop is very, very easy because we can get it from the calculation of the friction factor. And again, it is in the table, and from the table, from analytical work, the friction factor can be calculated as 68.36 divided by the Reynolds number. What is very important to realize is that this is for fully developed flow. So this friction factor is only going to be valid for this part of the flow. There's no other information in the textbook that we can use to take into consideration the developing flow. So again, this is going to be an assumption that we're going to make that the friction factor is a constant over the total length of 40 meters. So the friction factor is 68.36 divided by the Reynolds number. It's equal to 68.36 divided by the Reynolds number of 1650, and that is equal to 0.04143. And then we can calculate the pressure drop as equal to the friction factor multiplied by L divided by D rho V squared divided by 2. The friction factor is equal to 0.04143. The length of the tube is 40. The hydraulic diameter is 0.3. So again, that is the hydraulic diameter multiplied by the density, which is equal to 1.204, multiplied by the velocity. The velocity we've already solved as of the air, which is equal to 0.0833 squared divided by 2. So that is the calculation of the pressure drop, and that gives us a pressure drop of equal to 0.02309 pascals. It is very, very low. Why is it so low? Because the volume flow rate is so low and the velocity is so low. Right. So now we've calculated everything that was asked for us. However, it is just now very important to realize that when we started with this problem, we've made an assumption, and that is to get the bulk temperatures of the air. And we've made the assumption that the outlet temperature is 30. And our calculations are showing that the outlet temperature is higher than we thought. So what we will have to go and do now is theoretically what we will have to go and do is we will have to go and calculate a new bulk temperature. And we can do it now by saying it is equal to the inlet temperature plus, and I suppose the more accurate of the two would be the approach 2, and that would then be an outlet temperature of about 35.83 divided by 2. And if we go and calculate it now, it would be 23 degrees Celsius. So what we're supposed to do now is to go back to the tables, and at a temperature of 20 degrees Celsius, go and get a new density at that temperature, a new Cp, a new K, viscosities, and the Prandtl number, all of them. And we have to redo all the calculations. So that's the one approach that we can follow. What I would have done rather is to calculate the new bulk temperature by saying it is equal to, we know that in this case we've got this type of temperature profile, so the LMTD gives a very, very good representation of the average temperature. So that would the LMTD be now, and that would be delta LMTD. Okay. So what I would do is I would rather use this LMTD to get an average temperature of the air, and that would then be to say it is equal to 40 minus the LMTD, and I'm going to use the LMTD of the second approach because it should be more accurate. So that would be 40 minus 13.09, and that would then be a new bulk temperature of 27 degrees Celsius, which is then quite different than the 23. And again, you can go and get the new values for the density, the CP, etc., all of them, and you can go and repeat all the calculations. And it is a good exercise to go and do that. However, if you're going to do that, you're going to find that all the all the values are about the same. And what's the reason for that? The reason for that is if we look at the properties of air, typically at 20 degrees Celsius, and if the temperature increases are in the order of 10, 20 or 30 degrees Celsius, then the properties do not change that much. This problem would have been totally different if the increase in temperature was maybe 100 or 200 or 300 degrees Celsius. Then there will be quite significant changes in the properties, and then if you go and redo the calculations, you'll totally get a new answer. So it is a judgment call that we all need to do, but what is very important to remember is that for the test or exams, I'm not going to expect of you to iterate this problem until everything is accurate to within 1/millionth of a value. You just need to finish the problem and just at the end mention to me that you know that you will have that you will have to reiterate this problem, and if you could maybe guess what will happen, like in this case for air, if you make the guess that, I mean, most probably there will not be a big change, then that would be great. And also, you know, if the problem is maybe if there's an increase of maybe a few hundred degrees Celsius, if you could maybe write a line or two there that you would actually expect that there will be significant changes, then that would be great. So that is the end then of this problem, which again, what is making this problem different than in the class of problems of internal forced convection is the fact that the wall temperature remains constant. Remember, when we have internal forced convection, then in general there are two classes of problems. The one class is where the wall temperature remains constant, and then we will have a temperature profile like that. It's not linear, it's an exponential one. While the other class of problem is a problem where we have a constant heat flux, and when we have a constant heat flux, then the temperature increase will be linear, but that we will do in a separate problem. So that is the end of this lecture. Thank you very much.